Okay, so we're at the computer now, where we'll demonstrate the partial discharge software. This is where all the measurements are done. The software is currently communicating with the PD coupler out there. Everything's connected. And once we load into the main menu of the software here, we'll see that we have one segment that we can go into, and it's called New Measurement Task. The other segments are blanked out. This is the software's way of walking you through the process, keeping you on track, and making sure you don't get ahead of yourself. So if I wanted to, I can go into New Measurement Task, pick any one of these existing cables, and do a measurement. For us, we're going to go ahead and build a new cable. We're going to start from scratch and create a brand new cable for what we're going to do. So I go into my cable manager portion of the software, go over to New, and now I have this header data that I must put in. So for here, I'm going to put in video demo cable. I have to put in the rated voltage of the cable, or at least the system voltage. So in this case, it's 8.7 kV. My location is in Dallas. I have my option between 3 single core, 3 core, or single core. Single core is actually what we're connected to here. It is just a single phase cable. 3 core would be a bundled cable where all 3 phases are in the same bundle. And what I'm going to do is pick 3 single core. This is basically 3 individual single phase runs working as a 3-phase circuit. But what this does for our purposes here is if I wanted to make a measurement without making a whole new cable, I can do that. So if there's a reason to just change something and go and make a measurement, I can go ahead and do that very easily here. I can put a comment in here if I wish. I need to name the near and far end terminations. They are air insulated with slip-on elbow adapters there. So that's my header data is all done here. Now I have to go over to sections, and basically what this is looking for is 2 things. Number 1, total length of the cable. We want to know pretty accurately how long the cable is overall, and also where the splices are positioned. If we don't know where the splices are, that's not the end of the world, but it is what we want to have. We can find that out by looking at our maps, our historical data. Maybe with a TDR we can find a lot of this information out. But we're on XLPE cable here. We have 4 splices, and they're about 64 meters apart. So I have my first section here, and you can see that it adds this section down in the bottom of the screen here. When I add another section, it puts in my splice. So I want to add this to the point where I have a total of 4 splices. This matches what's on our cable. We can see the specific data for each of them. My first segment is from 0 to 64 meters. Next one is 64 to 128, and so on. I click apply, and I click exit. We're done with the cable manager for now. Now I need to make a new measurement task. So I go here, and I come down here to video demo cable, the one we just selected. I can double click that. I can tell it if I'm on the near end or far end by clicking these toggle buttons here, and I click apply. Now we'll see that the next segment has opened up, and this is my calibration segment. That's already connected. It's set to negative impulse of 1 nanocoulomb. So I want to make sure that my charge rate here is set to 1 nanocoulomb. And then I click start. The first thing I want to look at is down the bottom portion of the screen here. I see this pulse train. So I see these very consistent, evenly spaced pulses going down the screen here, and they're all about the same height. So this is telling me that my injecting device is well above the noise level, and it's injecting a consistent and good pulse. Once I see that, I look at the top screen, and here I see that my software has automatically tagged the initial pulse right here on the left-hand edge of the screen, and it's automatically tagged the reflected pulse. So this is the pulse that's traveled down the length of the cable, bounces off the end, and comes back. And we can see that our total calculated distance is off by about 11 meters, or our cable speed is off by a little bit. But this is good enough for our purposes. I want to make sure that I save my calibration. When I click exit, it'll remind me to disconnect the calibrator, so I'm going to do that right now. The calibrator is not a high voltage device, so if you leave it connected, you will kill it. I like to personally hold the calibrator in my hand when I click the OK button. So the calibrator is in my hand. It's on the equipment now. Now the next segment has opened up, the measurement segment. I click into there, and the first thing it does is going to connect to the PD coupler. Okay, and it's made its connection. This has been sitting here for a little bit, just idle, so it took a little bit to wake everything up. So I go ahead and make my measurement of my noise level, and we see that it's pretty good, nice, consistent, fairly low level. There's a couple of small disturbances going on out here, but we're looking at a level of about 20 picocoulombs. That's pretty good for field level. So I want to save my disturbance level here. That automatically puts me into the measurement mode. And what I might want to do is just kind of precondition this cable a little bit, put a little bit of voltage on here to start. Opinions will vary on this amount. Press green button for go, but we don't know how long this cable's been sitting out here. We just want to put some voltage on it, kind of warm everything up, so to speak. And we are actually already seeing some PD events here. We're not going to save these warm-up measurements, but we will eventually come back to this and recover this data later on. So I set it to do 5 shots just to warm this up. We have 2 shots remaining. And while that's running, I should point out some other portions of the interface here. We see that we're on phase 1. We have a drop-down menu. We can change that. Our amplifiers are in the range of 100 picocoulombs. If our measurement goes much above that, we start saturating the amplifiers, and we have to give it a longer range. We can go into mode here. We have our damped AC mode, which is what we're in now. We have our cosine rectangular mode that we can vary the voltage on. That's called slope. And we have our cosine rectangular mode that has a fixed voltage. That's called CR mode, VLF CR test. So we've done our last shot here, and these drop downs are now available to us. We can change the number of shots we do. So I'm going to set it for 3. We can limit the maximum voltage we apply to the cable. It's really just kind of a safety belts and suspenders kind of thing. If you're careful and have everything done correctly, there should never be a real need to use this. Right now we're set into multiples of rated voltage mode, so 1 times rated voltage. We can also set it to RMS mode or peak mode. But if we leave it in multiples of rated voltage, this kind of normalizes everything across your voltage ranges. So no matter if I'm on 15 kV cable or 35, if I apply 1 times rated voltage, it's always the same. Down here, it tells me that I've measured my noise level. I have not measured my inception voltage, my extinction voltage, or have any other measurements yet. So what I want to do now that I've kind of warmed the cable up, go back to about half rated voltage and start the test. So we've done a couple of shots here. It's a little bit difficult to pick out what's going on in this this example. There's some PD going on. As we bring up the voltage, this will become a little bit more obvious, but there is something going on out here. So we're going to leave that. We're going to make sure we save this measurement. And we'll start raising our voltage up. In this case, to 0.7 times rated voltage. We'll do a couple of shots there. So the reason that we're slowly raising the voltage up is we want to see at what voltage we start to see some partial discharge. This is just some noise going on out here because there's no voltage here. It can't be partial discharge. It could be from a cell phone or something. There are a couple around here, so it's hard to tell. And what we want to do is start raising the voltage up until we start seeing some PD activity. So let's save that and let's go a little bit higher. Let's go to rated voltage. And unfortunately right now there's no standard or real strong guide on PD measurement techniques, so everybody has slightly different ways of doing it. I think that the important thing is that you follow the general idea of building up voltage step by step, looking for that inception voltage. This software does a pretty good job of walking you through, but for example, somebody may choose to do only one shot at each voltage instead of 3 like I'm doing. There isn't a strong standard on that rate just yet. So I think that this is still noise, most likely, because there was very little PD on the first pulse here. Usually if you see something on the first pulse, or you would more likely see something on the first pulse rather than the second. So let's build up the voltage a little bit more. We can always come back and redo these voltage levels once we see what's actually going on the cable. So here's my first real positive PD. I'm seeing a lot of PD on the first half cycle of the waveform here. So I'm very sure that this is some PD. There might have been some before. It's kind of difficult to say with what the way the waveforms are showing, but this one is for sure some partial discharge. So we don't know. Now, we didn't see this same example at rated voltage, but we did see it at 1.2. So we're not quite sure if 1.2 is going to be our inception voltage or not, if that's the lowest voltage we start seeing this at. So I bumped this back down to 1.1 and redo the measurement. If we still see this same kind of signature at 1.1, then we can call this our inception voltage because we didn't see it at rated voltage. And what do we see here? Let me wait for the next shot to come in. So I would call 1.1 our inception voltage, especially this shot. We have some really strong PD showing up on this first half cycle of the wave. And let's see. So we'll save our inception voltage here. So you can see that we now have another check mark in our box here. Now we need to try to hunt for the extinction voltage. So we have to put our voltage up a little bit above where our inception voltage was and allow it to kind of self-extinguish. So that's pretty obvious. We have some PD here, some here, arguably some here. So this will probably be our extinction voltage. We'll see what happens after the third shot. The other thing we're starting to see is our PD map is starting to come in. That's the upper part of the screen here. And it's telling us that our third splice here is having some problems. And I know that the lines aren't exactly lined up, but that's very common. We don't really expect to see partial discharge in the insulation material itself. It's much more expected that we see PD in the splice, and it's much more reasonable to assume that our distances are just off by a little bit. So we see some PD here. I think that this is our last PD inception PD voltage, so we're going to set our PD extinction voltage. Software does not do a good job of finding it this time. We're going to drag our cursor back over in this direction, put our cursor right on that line. Come on, there you go. And save our PD extinction voltage. Okay, so now we've got our check marks. We've got everything we wanted to do. We're starting to see, or our software is locked into this splice. The only thing left to do is to bring this up to our final voltage. In most cases for age cable, that'll be about 1.7 times rated voltage. For new cable, that'll be about twice rated. We're going to call this age cable. And we're going to do a couple shots. What we're trying to do now is just create this map. Try to really home in on where the partial discharge is occurring from. You'll notice that over on the left-hand side, I'm getting this warning that my amplifiers are saturated. So I can just increase that. I don't need to do any recalibration. That was all done at the same time when we did our calibration step. Some other pieces of information that we're starting to see on our screen here. Our maximum charge is just over 3 nanocoulombs, which is quite a lot. Our test voltage is done at 21 kV. We have a frequency of 400 hertz. And our remaining shots, we have 2 shots remaining in this test, in this sequence. So there is an option in the software. By default, it pops up with a box every time you go to take a new measurement. If you don't save the measurements, it will erase them. We do this because these files get very big very fast. Right now, this particular software, that dialog box is disabled, so I want to make sure that I manually save my measurements here. If this was an age cable, we'd probably be done. We know that this third splice is a problem. If we really wanted to, we can try to investigate this splice a little bit more by putting more shots on there. If it was a new cable, we'll go up to twice rated. So we'll do that and see what kind of results we get at twice rated. We'll do a couple of shots there. So in this voltage range, we're starting to see more activity on that first splice. So it might be interesting to let this run for a little bit and try to get enough activity that the software can do its statistical analysis and lock in on that first splice. And that's hopefully what we'll get at the end of the 5 shots. We can always put more shots on here. Damped AC tends to be very gentle on the cables. If not, we can switch over to cosine rectangular. That's a little bit more aggressive. It's a little bit better at triggering PD. Triggers PD at a little bit higher level, which makes it easier to detect. I'll make sure to save these measurements. And like I said, what we can do is go over to slope mode. And it automatically disables high voltage on that switch. I can start, press the green button. And you can see that this is starting to build up voltage. We're up to 12 kV now. It'll take a couple of seconds for it to get up to the operating voltage that we want it to be at. And once it's there, we just let it flip back and forth, cycle back and forth a number of times to get our results. So, my goal in trying to do this is, what I'm trying to do is get that first splice, the one about 64 meters, to populate a little bit more, and for the software to be a little bit more sure that that's where the PD is actually coming from. And we're starting to see some more dots populate that area. So basically, every time this switches polarity, we get some more data coming in. And even if the software doesn't lock in on that first splice, we can manually do it in the reporting mode if we wanted to. But it would be nice to get the software to do it itself. And we're starting to have some snaps inside the box here. That's what these overflow ranges are. And we're also starting to get some partial discharge on the termination. So we might not be able to get this without having a breakdown inside the box. We're having too many flashovers inside the box. We're not going to be able to get this to lock on for us today. That's okay. So, if we wanted to, it would be very easy to switch over to our next phase. That's why I left this as the 3 single core option. You'll see that it resets our voltage for us. We can go into damped AC if we want and do this whole test over. I only have this one phase set up for partial discharge testing, so we're not going to do that, but that's all you would need to do in the field is switch over to phase L2 and just start to test over. It's actually not necessary to remeasure the disturbance level even. You just go right into the measurement step. I do want to save all those measurements. See, this is where that dialog box is helpful. It actually wiped off all my measurements that I just did with that cosine rectangular. So, that's okay. We could redo it if we wanted to, but I think that we see our results here. I'm going to exit this measurement mode, and you'll see that the next segment here is report mode. And this this screen is our histogram screen. It gives us basically a count of the number of events that it records at each position. So we'll see at this position it only recorded about 5 events or so. At the position at 198 meters there, it recorded quite a few, over 50, so maybe a total of just about 100 events. Our cable plan, this is where we compare the splices. It's nice to already see these dotted lines representing the splices on the screen, but it shows us our cable. If we had different types of insulation in there, that would show up here as well. This is all XLPE insulation, but this is where all our splices are. Localization, I will come back to that in a minute. QUQT, basically this is our, if I highlight some events here, we'll see that these are heavily biased towards the positive polarity, but that's kind of expected with damped AC, especially the way we noticed that all of our first cycles were positive polarity. So if we wanted to be thorough, we would run an equal number of positive and negative polarity damped AC cycles to even this out. So the way we did the test, this might not be very significant. We can write a recommendation here, recommendation, recommendations, comments, etc. I missed an N. And if we come back to the localization tab, if I were to pick one of these dots here, one of these blue triangles, what we'll see is the actual measured pulse that the software measures. So here's our initial pulse coming directly from the event, and here's the reflected pulse that goes from the event, bounces off the far end of the cable, and then reaches the PD detector sometime later. This is the initial pulse reflecting off the far end again. So here's our calibration curve in this greenish brown color, and here's our initial pulse from the calibration. There's the length of the cable, and there's that initial pulse bouncing off the far end. So we can't possibly have an event that occurs outside of this box. So that's one way that the software verifies that these events are real. As we look through, so there's another good measurement. The software tags the initial pulse and the reflected pulse. These all look real and they all look good. We can come over here. Oops, I have to pick a single point. And this one, it's having a bit harder time of identifying this because it's a little bit closer to the noise. This is only in the level of 75 picocoulombs. It's not too high above the noise floor, so it's a little bit masked by the noise. But these do look like pretty reasonably good results. What we could do is come around here and change this from a maybe result to a valid result. And if I change all of these, because they all look pretty good. Here's my initial pulse and my reflected pulse. So this is the manual analysis of the results that we can do in the reporting section. One other thing to note here, so we didn't do any measurements on phase 2 or 3, so we can eliminate those. I can eliminate phase 1 too if I want, but it's what we're looking at, so there's no reason to do that. Right now it's showing me the maybe results, and I just went through and fixed all those, so there's none left. We can also get it to show us the I don't think so results, and right now there's only one that shows up, and that's over in this area here. And if I click that, it's not so sure because yeah, it's not a very clean result. We can probably play with this this measurement here and get it to lock in. Just play with it a little bit. So now the software, now that it has enough statistical points, it's locked into this splice, this first splice. It did require a little bit of manual adjustment, but that's okay. We can see here, we can tell a couple of things. First of all, I want to limit where my voltage is. So I want to look at PD events that only occurred at or below rated voltage. So I do that here. And we can see that my splice at 198 meters was already exhibiting those events. And it was all the way down, it started showing PD events immediately. So those PDs that we saw at half rated voltage, those were valid results as well. They were difficult to look at, difficult to spot above the noise, but they were valid. Once we get up to rated voltage, we see that only one of those two problems exists. So that means that just by voltage, this is a more critical issue, this splice number 3. We don't start seeing PD on this first splice until about 1.4 times rated voltage. So that's a lot less critical just by the voltage that we're looking at. Also, this splice at 64 meters is a lot less critical because it exhibits a lot less picocoulombs. We're looking at a maximum of about, let me zoom in a little bit here. But what are we looking at? About 50 or 60 picocoulombs. So it's not that high of a level. Whereas this one is up in the range of 2 nanocoulombs at most, and most of them are in the range of as much as 500 picocoulombs. So this is a much more concerning, much more significant problem out here at 200 meters. We can eliminate one of the problems by having these extremely high values is it kind of squishes everything down. So we can limit the values that we look at so we get a little bit more space to work with here. They're still there, they don't go anywhere, but we're just not looking at them. So it stretches these out a little bit, makes them a little bit easier to work with. Those extremely high values are easy to spot and maybe not all that interesting. The last thing that we can do on this screen here is we can pick one of these dots. And maybe that one's not so interesting. Maybe I need to pick a single one. Try zooming in here a little bit. Pick one that's a little bit interesting. Again, try to pick one. Sometimes it's difficult. Okay, maybe this one's a little bit interesting. Maybe I have doubts about this one. I'm not entirely sure if the software did a good job on it. Well, I can take this measured PD event and add it to my report. So that'll show up in the report. So when I'm all done, when I've done my analysis and any manual corrections I needed to do, I can come over to print report. And there's a template here. And basically, this is our default template. If I want to make changes, I have to make my own template. But I can change a lot of this. I can't change anything in default, but it is all available to be changed. We just have to make a new template, which I'll show you in a second. So I can change my address, my company logo, my cable data. I can include it or not. I'll show you what that looks like in the report. I can include my recommendations. If there's any customized text I want to add here, a disclaimer, any legal stuff, confidential, things like that, we can add that kind of thing. IEC table, we can choose to include it or not. I'll show you what that looks like. I can include my calibration for all phases, or just one phase if I choose. I'll come back to PD mapping. Selected diagrams, these are the ones that I just put in here, this one here. I can choose to include it or not. And finally, PD mapping. The default template is basically, it's going to have 8 charts in there. A chart from 0 to rated voltage for all phases, for phase 1, phase 2, and phase 3. And from 0 to maximum voltage for all phases, phase 1, phase 2, phase 3. It'll be a total of 6 charts. If I wanted to adjust that, if I didn't need them all overlaid, if I didn't want to include this all phases thing, well, I can't do that on the default template. I have to create my own template. But I can add and subtract things. If I only wanted to see things from rated voltage up to maximum, I can make that chart as well. Or if I only wanted to see things 0 to 1.3 times rated, it's very easy. I just click here. I can show you how to do that. Create a new template, come down to PD mapping, and I can set that from 0 to 1.7 for all phases and not include an individual chart for my 3 phases. I can go 0 to rated voltage. This one should have saved. Sorry, I need to do it that way. So 0 to 1.7 for all phases overlaid. My 0 to rated voltage, maybe I just want to have all 3 phases individually. I probably want to have one 0 to max. I can have all phases overlaid and then the 3 individually. It's very customizable no matter what, including the maybes, include the I don't think so's. It's very customizable. When I'm all done, I click print PDF. And we can see it's working over here. The bar's almost full. It'll pop up in just a second. And what we can see here, this is all the cable data that we put in to begin with. Video demo cable, cable number, rated voltage, things of that nature. Near end, far end, switch gear. Here's our cable plan with the splices laid out on it. Nothing too exciting here. This is the cable data. One of the things that we can, just the cable plan. One of the things that we can take off the report if we choose. The segments, like a numerical kind of representation of each of the phases. Here's the IEC table. Here's my recommendations. So if I wanted to put something in, replace this place at 198 meters, I can put it in that section. Here's my IUC table. This is kind of like a summary for the whole process. So my background noise was 20 picocoulombs. My PD inception voltage was 9.6 kV. It was actually probably less, but we weren't too sure. This was not the clearest example we've ever seen. My PD extinction voltage was 3.5 kV RMS. My PD max, my picocoulombs at inception voltage was only 57, so it's very low at my inception voltage. My PD max at rated voltage was only 300 picocoulombs. It's pretty low. My PD max at 1.7 times rated voltage was 13 nanocoulombs. That may have been something on the terminations that we were catching. And my PD max at 2 times was about 1 nanocoulomb. That was probably in the splice itself. My frequency was 400 Hertz in damped AC mode. There's my calibration pulse. Nice capture there. There's my PD mapping for phase L1, 0 to rated voltage. So I can see that at rated voltage, I had some problems on this splice right here. Number 1, important positions. Number 1 at 197 meters. So that's an important position. It tags those for you. I didn't do any work on phase 2, so there's nothing to report. And similarly, I didn't capture any data for phase L3, so there's nothing to report. Mapping for 0 to 1.7 for all phases. And it gives me my results in that. Basically my histogram up here and my mapping down here. Important positions, again, that point at 198 meters. And mapping for 0 to 2.1 times rated voltage for all phases. So this is just kind of the things that we set. Here's my phase L1, L2, L3 for that. Kind of the things we set. The default is actually pretty good. Gives a pretty good summary of everything without being overly complicated. And here's that pulse that we wanted to take a look at, the one that we added to our report. So that is reproduced here, and if you wanted somebody else to take a look at it, or you were unsure, whatever reason you wanted to include it in the pulse here, just as an example, saying this is the one at 197 meters. For whatever reason you want to include in the report, you can include it. And that's the end of the report here. We can file, save as, and save it to whatever directory we want. Or, close this. I'm going to exit the reporting software and come over to my cable manager, go down to my video demo cable, click in here, measurement tasks. It actually saves the report for me. So this is included, this is saved inside the database software. The PDF report is saved. And I'm just going to pick another cable here. I have no idea what this is. Pick it, load it up here. And you'll notice that my calibration and measurement segments are empty. It would allow me to make a new measurement on this cable. So once I build the cable into the database, I don't have to build it up again. It's saved in there. But now I can go to the report, and you'll see that this is all the data that was recorded on that cable, the one that I just pulled up. And according to the timestamp, it's from February 2017. We're doing this in June of 2018. So this is just saved on this laptop, and I can do all the same manipulations on here that I was able to do on the test that I just completed. Word of warning though, these files do get pretty large pretty quickly, so you may find that you just can't save all the data. You may run out of hard drive space quickly. And if I wanted to, I can create a report from this old file as well, if I so desired. So that's it. There's not too much to talk about in settings. That should be set it once and forget about it, so I'm not going to cover it. I come over here, I exit. It reminds me to de-energize and ground the system. Yes. I can always put the emergency lock on my equipment. And that's it. That's the software. All that's going to be left now is to clean up all the equipment. So I'll start working on that. Thank you guys for your time. If there's any questions, please reach out to us. You'll find our contact information on the website. And we'll always be happy to help you. Thanks.